Good evening, my name is Trevor Thomas. I'm a project geologist for Royal Resources working on their Razorback and Ironback Hill and surrounding iron ore prospects hosted in the BRAEMAR Iron Formation of the Untitled region of South Australia. As you said, this is my first professional presentation. I was thrown to the sharks by my boss Gavin England sitting in the back there. So if you have any overly technical questions, rest assured Gavin will be around for the dinner and you can think about a few brutal questions for him. He's got thick skin. Tonight I'll be talking about geology and some recent developments we've made on our Razorback and Ironback Hill projects. Quick disclaimer for those who can speed read. This talk is intended as a geological/technical presentation. So in South Australia, Royal is developing its iron ore magnetite deposits in the Yunta area, about 300 k's northeast of Adelaide. It's a low-grade, high-tonnage bulk commodity, very well placed in terms of infrastructure and processing. So why Razorback? Well, we believe that Razorback differentiates itself from other Australian magnetite projects in a number of important ways. Namely, the deposit is not a banded iron formation. It is hosted in the BRAEMAR Iron Formation, a predominantly magnetite hosted in a siltstone. And as a result, metallurgical testing has confirmed that the ore is soft, having relatively low crushing and grinding costs. And we found that the ore breaks along crystal, along grain boundaries, not across the crystal faces. Therefore, we need less than half the power than it would be to actually crush an ordinary BIF. And it's located in an infrastructure-rich area, close to open access, high-capacity rail, a selection of ports and to gas, electricity, labour and engineering services. As well as that, we have a lot of ore, a lot of potential for ore as well. We have over 110 kilometres strike length prospective for iron within our tenements, with a potential of 4.5 to 8 billion tonnes iron ore. To date, we've announced a global JORC inferred resource of over 2 billion tonnes at 21.7% Fe, with just under 1 billion tonnes at JORC indicated. In addition, Davis tube recovery work shows that the ore is capable of producing a very good concentrator, around 66 to 68%, but we do get over 70 in places with very low deleterious elements, but more on that in a minute. Also in terms of extraction at Razorback, given the deposit outcrops and dips shallowly at between 40 and 50 degrees, to the north it will have a near zero initial stripping ratio with low OPEX, and together with existing rail infrastructure and whatnot, CapEx should be low, ensuring that we should be fairly competitive. So a little on the geology of the deposits. The BRAEMAR, the magnetite-rich host rocks of the Razorback and associated iron ore prospects of the BRAEMAR Iron Formation are located within the NEOPROTEROZOIC basal sediments of the Umbertana group within the Nakara Arc region of the Adelaide geosyncline. This sedimentation coincides with the Sturtian glaciation about 750 to 700 million years ago. And the BRAEMAR is thickest in the Barata Trough, a fault-bounded basin located in the Yunta-O'Leary region of South Australia. Previous workers on the deposits suggest that the BRAEMAR Iron Formation was a result of chemical precipitation during interglacial, post-glacial periods and formed in the coastal fringes where terrigenous influence was strong, so definitely a detrital component. And we see similar deposits throughout the world as a result of this ocean anoxia magmatic activity in restricted basins that you see during the NEOPROTEROZOIC. Two that bear particular similarities to ours are those of the Damara origin in Namibia and also the Yobel Formation in Uruguay. Witten, who conducted a study on the Razorback on Razorback Ridge in the 60s for the South Australian Department of Mines, suggested the BRAEMAR Iron Formation occurs at the top of the main glacial sequence and comprises of interbedded, interlaminated iron formations, bedded iron formations, and tillitic iron formations. In the area around the Razorback Iron Project, ironstones of the BRAEMAR iron formation occur as prominent outcrops and are interbedded with diamictites, dollarstones, sandstones, siltstones, and magnetiferous siltstone. Regionally, it's easily mappable and with aeromagnetic data. And regional deformation and faulting and folding occurred during the Delmarian orogeny around 500 million years ago, resulting in open to tight folded patterns aligning in a northeasterly orientation. The Razorback Ridge iron deposit is positioned on the north dipping limb of the Pielko anticline, and that's the Pielko anticline running through there, with Razorback forming that northern limb. It dips around 40 degrees, while the Ironback deposit forms the southern limb, dipping a little steeper at around 60 to 70 degrees to the south. Witten in the 60s divided the BRAEMAR iron formation at Razorback into 7 sedimentary packages, members A to G, with a total thickness of between 480 to 780 meters. Of these, members A, B, and D and G are of economic interest to us, and all outcrop its surface, with Unit B forming the prominent ridge that is Razorback Ridge. And here's just a bit of a cross-section where this is our main economic ore horizon, Unit B, followed by some interstitial material, and a Unit D. We'll go into in a bit. And here we have an aeromagnetic image of the BRAEMAR Iron Project area, displaying that 110 kilometers worth of iron-bearing strike. To date, the work has focused on Razorback and Ironback. I guess the important point is the fact that the resource is still growing, with a great deal of prospective strike yet to be drilled. And here you can see our path of resource definition over the past 2 years. The blue polygon was our first resource, followed by the red, marking our westward progression to the western extent of Razorback, which we've called Razorback West. And to the east, we've got the interzone and the Iron Peak, which we're currently working on. Currently at Razorback itself, we're sitting on 1.5 billion tonnes at 21%. Of those mineralized units, at Razorback and Royal, we've further divided each member into their respective lithological divisions. For example, the most economic member, Unit B, has been divided into 3 easily recognized subunits, namely B1, B2, and B3, working stratigraphically upwards. Unit B1 is characterized as a bedded magnetite-rich siltstone with minor thin beds of dolomitic siltstone and fine sandstone. And here's an example of the core. That's HQ core, where you can see that soft sediment deformation. Unit B1 is overlain by Unit B2, a tillitic diamictite ferruginous siltstone with varying dropstone content. And you can see the lith fragments there, mainly composed of metasedimentary and granitoid lithic fragments. This is overlain by Unit B3, an interlaminated iron-rich siltstone, much like Unit B1, but with increased siltstone and sandstone interlaminations. And you can really see the soft sediment deformation, a little bit of cross-bedding in there, and what have you. These lithological divisions are marked by well-defined contacts between the units and are duplicated in other members as well. For instance, the Unit D member is pretty much just a duplication of that unit B, where you see the bedded followed by the tillite and the interbedded. So the mineralogy. At Razorback, as described, there are two main facies types that make up the ore horizons. The first being the tillitic diamictite ironstone and the other being the laminated bedded ironstone. While macroscopically the two facies appear quite different, compositionally the iron-rich components are very similar. The ironstones are typically fine-grained and are composed of magnetite, hematite and quartz with lesser amounts of sericite, chlorite, dolomite, feldspar and apatite. The non-ferruginous bands within the bedded interlaminated siltstone consist of quartz, biotite, dolomite, plagioclase, sericite and chlorite with minor amounts of hematite and magnetite. The two predominant iron species, hematite and magnetite, consist of one individual idiomorphic shaped magnetite grains in the size range of between 30 to 120 microns in diameter, and to the microcrystalline hematite grains usually below 10 microns in diameter. And here we can see a reflected light sample of laminated iron ore from Unit B at Razorback. You can note the subhedral to euhedral magnetite grains which mark these brown-grey unit crystals with a finer matrix of hematite, these little white ones here, phyllosilicates and quartz marking these dark grey crystals there. To date, our studies using LA ICP-MS have shown that the magnetite to be pure, with none of the analysed elements enriched to more than 100 ppm. Given the small grain size of hematite, only semi-quantitative quantitative analysis was performed with SEM-EDS, which showed that hematite may contain titanium in the order of hundreds to 1,000 ppm. We also see martite as a third iron species, which are replaced magnetite grains predominantly in the near-surface geology, as you might expect. Some work that we've had done has also found from 3 cores from Razorback that higher magnetite grains were linked with finer parts of the lithostratigraphy, and the coarser, sandier parts contained less magnetite, and this could be cross-correlated between holes across the deposit. This disparity between the two grain sizes and mineralization could be potentially dictated by the O2 fugacity in the sedimentary pile during early diagenesis. And the next stage of that we're looking to do is actually working out the timing of this mineralogy. And here you can see one of our lith logs of our holes at Razorback and the correlation between the downhole magnetics and the lithologies, displaying the stratobound nature of the magnetite, where, as per those images before, you have Unit B1 as probably the highest concentration, and followed by Unit B2, the tillitic ironstone, and B3, the interlaminated ironstone. Across the deposit, we're finding our magnetite recoveries coming in at around the 15 to 16% mark at an average, and that's at a 45 micron grind. And with that, we're getting 66 to around 69% iron concentrate, and we do have examples that go over that as well, at around 70. We're also finding that DTR is showing similar figures to global mass recoveries. A complication that has arisen out of the DTR analysis is that of the recoverability of those grains that have experienced some degree of martitization. Our metallurgists have found that given the magnetite component of these grains, some proportion is actually recoverable, adding to the resource recoverability. And here you can see a picture of that martitized grain, where you get the magnetite has slowly been replaced by the hematite, this finer, giving this pretty spectacular texture. There's evidence of martitization of some magnetite grains to hematite. a definite increase in the concentration with samples near surface or in paragenetically later fracture zones. Preliminary work on DTR versus MagSUS has shown that the use of magnetic susceptibility measurements made both at the laboratory and downhole may be suitable, may be a useful substitute to DTR recovery. This should hopefully go a long way to reduce the costs and give us a better picture of the distribution of magnetite recovery over our deposits. We've found that there is a fairly robust correlation between DTR recoveries and MagSUS grade, and potentially, given a calibration factor, we may be able to use MagSUS to effectively map the distribution of magnetite. So far, we generally see that diamond core has a much better correlation than RC. Most metallurgists hate the concept of DTR and RC, and mainly due to a few factors inherent in percussion drilling, namely overcrushing and overgrinding, contamination, and heterogeneity issues. Something else we've noticed is that DTR often picks up and recovers the martite grains, given their magnetite component. However, MagSUS's effectiveness is somewhat marred in the face of martite. We're looking at overcoming this by subsetting those near-surface oxidized zones and treating them separate entities. So we've embarked on a work program to use our downhole magnetic MagSUS data to map out the magnetite within the deposits, much in the same way as, for instance, one might use an EU308 disequilibrium factor. In terms of the pre-feasibility, well, we're finalizing a lot of the finer points. I don't want to preempt the actual results of that study, but safe to say we're, at the moment, we're finalizing our pit design given the recent update to our deposit. We're looking at finalizing our processing plant and tweaking and looking at the economics of the hematite recovery aspect. We're looking at the transport options, whether that be a slurry pipeline or a train line, with slurry looking like the preferred option at this point. When it comes to water, we're looking at the possibility of a desalination plant. And in terms of power, we could either go via the gas or the transmission line options. And we're getting out into the community. We have a stakeholder engagement guy that works for us, so Jamie Love, and he's getting out there. Finally, in terms of transport, as I said earlier, the slurry is the preferred option, with slurry all the way to a floating stockpile platform out in the Gulf being the preferred option at present, mainly because it should reduce OPEX in that with the slurry pipeline we could potentially have a desal plant with a return pipe to recycle and reduce costs.